So each of these problems has a couple different ways to be thought of. The first one's pretty easy. How far is it from here to here? 270 plus 15 more, 285 degrees. Okay. What do I know about the second problem? It's bigger than 360 and it's negative because we're going clockwise. So from here to here is 360. So negative 360 minus another 180, and then how far from there to there? Another 60. So that would be negative 600. All right. Radians seem a little bit tougher, but actually radians are easier for something like this. Well, not always, but in this case they are. How far is it from here to here? 5 pi over 5, and then I need to go an extra 1 pi over 5. So 5 over 5 plus 1 over 5 is 6 over 5. Okay. The last one's a little bit harder. What makes it so difficult? Right, whenever you have an angle that is offset from the vertical axis and the denominator is odd, then your fraction is going to have a decimal inside it. So, how far from here to here? 7 over 7, and then to there. 14 over 7, and then to there. Another 7, which would make 21 over 7. Well, this axis is halfway between 21 and 14. So 3.5 more than 14. So the positive y-axis is 17.5 over 7. How much more than 17.5 over 7 are we looking at? One more. So 18.5 over 7 pi. But we don't want fractions. We don't want decimals inside our fractions. So what should I do? We could double the top and the bottom. You could also plug it in your calculator. If you did 18.5 over 7 math fraction, it's going to get you 37/14. Is that right? Somebody in first period did something that I thought was really smart that I'd never thought of. He went like this. Let's just count it in terms of pi. 1, 2, 2.5, plus 1/7. So he just typed in 2.5 plus 1 over 7, and he ended up with 37 pi over 14. So that would work. You could convert it to degrees. So we could convert this into degrees. The trouble is it's going to be a rational number. It's going to have a long decimal. And then you could do 180, 360, what would that be? 450. So 450 plus whatever pi over 7 is, which is going to be, I don't know, like 52 point something degrees. And then you can find out what that is, and then you convert it back. But if you do that, you have to make sure you use all of the decimals. If you leave one decimal off when you try to convert back to a fraction, if that decimal isn't totally perfect, then it's not going to give you the correct fraction. If you shave one decimal off the end, then you won't be able to get back into fraction form. The decimal form will be really close, but the fraction form won't exist. Okay. Let's do another quick review. Where does 198 degrees land? Quadrant 3, because bigger than 180, less than 270. So on your worksheet last night, you were supposed to draw the angle. I hope you didn't try to be very exact. Technically, this angle is right here, but if you wrote it right there, that's all that matters. As long as you get the quadrant right, then all the pictures we're going to draw in the future will work. So all that really matters is that you're in the right quadrant. if you want to say, well, 198 is closer to 180 than it is to 270, so I'm going to put it close to 180, that's great. That could help you reason some things out. But as long as you're in the right quadrant, I'm happy. All right, what if I turn that into a decimal? 198 divided by 360. What does that mean? 55%, which is between 50% and 100%. So in degrees, the decimals are 25%, 50%, 75%, and 100%. And I know we've done this over and over, but we can't state it too many times. So 55% is just bigger than 50%. Well, what if I had, let's see, 6 pi over 11. What quadrant is that going to land in? Well, let's look at the decimal. 6/11 is 54%. Where does 54% land? Quadrant 2. Why 2 and not 3? Well, the first problem we did, 55, so the 198. 55% of what? Of the whole circle. So when you're dealing in degrees, 198 degrees is the same as 55% of the circle. But when I'm talking in radians and I have 54% of what? What did you say? Half a circle. How come? Well, it's 55% of pi, or 54% of pi. And pi is half of the circle. So 6/11 would be 54% of pi. So this is 100% of pi, and this would be 50% of pi. So 54% would be in quadrant 2. And you need to keep that separate. The decimal percentages are out of the whole circle, or sorry, the degree percentages are out of the whole circle, and the radian percentages are out of pi, which is half a circle. So in degrees, if I had 6,542 degrees, and I divided that by 360, what does the 18 tell me? 18 revolutions. Do I care? No. What does 17% tell me? Quadrant 1. So that would be in quadrant 1. If I had a really big radian, 67 pi over 4, 67 divided by 4, what does the 16 tell me? Right, it's not 16 revolutions. It's 16 pi's. So if I count the pi's, notice 1 pi is on the left, 2 is on the right, 3 is on the left, 4 is on the right, odd, even, odd, even. So it's even from here to here, and it's odd from here to here. So the top half is always even, and the bottom half is always odd. So 16 is an even number, so we're looking at 75% of the top, which lands in quadrant 2. Okay? Well, what if I had 89 pi over, negative 89 pi over 9? Negative 89 divided by 9. What does that tell me? Ooh, wait a minute. Top or bottom? Right. Negative numbers are backwards. Normally, a 9 would be on the bottom because it's odd. But now we're going in the other direction, so the bottom half is even and the top half is odd. So it's 88% of the top, which lands in quadrant 1 because we're going backwards, right? So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. and 88% more is going to place me in quadrant 1. Do we kind of have a handle on that? Is there anything you want to go over that you've seen so far? No? Okay. So, today we're going to talk about what are called reference angles. And I want to review radians really quickly. So we've decided that when we have our dial, the dial is going to be length 1. Okay? And when we trace out that circle, the radians are 2 pi. Now that 2 pi has a double meaning. 2 pi is the amount of rotations that we create. What does it also mean? A radian is a rotation and a what? A length. So the length of that arc, which in this case is a circumference, the distance that the dial travels from starting position to starting position is 2 pi units. Now in quadrant 1, we can create a 30-degree angle. And notice the length of the ladder is 1. Why do we like the ladder length 1? Okay, if you write it's easy to use on the test, I'll mark it wrong. The side length is equal to the percentage. So at 30 degrees, the height of the wall is the sine, and the length of the ground is the cosine. So sine is wall, cosine is ground, and the percentage is the height. So if I took the sine of 30 degrees, I get 0.5. So at 30 degrees, the height of the wall is 0.5 ladders. Right? And no matter how long your ladder is, if it's 8 feet long, we don't care. We throw out the 8 feet and we call it 1 ladder, or 1 radius, or 1 radian, or 1 unit. As long as it's 1, we're happy. So the cosine of 30 is 0.86. So at 30 degrees, the length of the ground is 0.86. Well, what are the restrictions on the domain for sine and cosine? How big can they be? Well, originally, in our triangles, if I called that theta, we could be greater than 0 and less than 90. But then we realized that this ladder picture still exists. If the ladder is straight up and down, then we have 1, 1, 0. If the ladder is flat on the ground, then we have 1, 0, 1. And we can still do sine and cosine. So we extended the domain to include 0 and include 90. Make sure I'm in degrees. Okay. But watch this. The sine of 137 degrees. That exists. That says that at 137 degrees, the height of the wall is 0.68 ladders. Well, that's a problem. Can you create a right triangle with a 137-degree angle? No, not at all. So, one thing we talked about when rotating angles is we don't care how you get to the terminal position. All we care is where you stop. What is a coterminal angle to 30 degrees? Well, we'd add 360, so 390. So technically, 30 degrees is the same as 390 degrees. Well, the sine of 390 is 0.5. Because as we take that ladder and we wrap it around, wherever the ladder stops, we draw our triangle and we measure the height of the wall and the length of the ground. Okay? Well, if I subtracted 360 from 30, I would get the sine of negative 330, which just so happens to be 0.5. So as long as the ladder lands in this position, the sine and the cosine will remain unchanged. Okay? So let's follow the wall as we move the ladder. And this is kind of hard to see. So here's my wall. As I rotate my ladder, the wall's getting taller until I hit 90 degrees. What's the height of the wall at 90 degrees? 1. So the sine of 90 should be 1. What's the length of the ground at 90 degrees? 0. So the cosine of 90 should be 0. What about into quadrant 2? So if I draw an angle in quadrant 2, where is the height of the wall? So if I were to draw a bunch of walls, let me switch colors. So I have little walls getting bigger and bigger and bigger till I max out, then I come across, that would be it. So right here, I'm looking at two different angles. This angle, and I'll give you one for instance, let's do 150 degrees. So if that's 150 degrees, what is my theta in the right triangle? 30. And theta is always the angle created from the ladder to the ground. So if my given angle is 150, then this angle is going to be 30. So the sine of 150 should be 0.5. What's the cosine of 150 going to be? Cosine of 150, wait a minute. Why is that? Why would the cosine be negative in quadrant 2? This height is 0.5. What is that length there? It's on the x-axis and it's on the left side, so it would be negative. So this would be 0.86. Okay, so we have two angles to look at. The angle measured in standard position is called theta. So this 150 is theta. Okay, but when theta gets bigger than 90 degrees, the triangle kind of destroys itself. So what we do is we create this smaller angle, which is called a reference angle. Ignore that. A reference angle. Now, reference angles have two qualities. First off, reference angles are always positive. So no matter where your theta lands, your reference angle is always positive. Because the only way to measure negative angles is to begin in standard position, and most reference angles don't begin in standard position. So they're always positive. Okay? And second, a reference angle is the shortest angle to get to the x-axis. So the reference angle is always the shortest angle that will get you back to the x-axis. So each quadrant has a specific reference angle. In quadrant 1, that is the reference angle. In quadrant 2, that would be the reference angle. In quadrant 3, that would be the reference angle. In quadrant 4, that would be the reference angle. Okay? And the sine and cosine for every reference angle remains the same. Sometimes it will be positive or negative, though, depending. So let's say, for instance, that I'm looking at 10 degrees. All of these reference angles are 10 degrees. So the sine of 10 is going to be 0.17. Well, if theta is 170, the sine of 170 should be the same. What would theta be in that case? Sine of 190, is it going to be the same? Well, we're looking at the height of the wall, right? So in quadrant 3, the wall is negative. Okay, and then how far from here to there? 350. Positive or negative? Well, the height of the wall is negative. Okay? So if I give you a particular angle, say 137 degrees, and that's my theta, what is my reference angle? Well, I recommend you draw the angle. Where does the angle land? Quadrant 2. So that's 137. How much more do I need to reach the x-axis? 43 degrees. How'd you find that? What did you type in? 180 minus 137. Okay? So what if my theta is 275 degrees? Which quadrant would that land in? Give me in 4. What's my reference angle? Well, 360 minus 275 is 85 degrees. And notice, reference angles are always positive. Okay? What about 300 degrees? Nope, no, that's not what I wanted. Let's do 200 degrees. Where does 200 land? Quadrant 3. So that would be 270, 200. What is my reference angle? Well, I need to get back to the x-axis, right? So how far do I need to backtrack to reach the x-axis? 20 degrees. Okay? All right, let's give you a hard one. 865 degrees. Well, so, oops, let me use a different color. How many is that? 360, 720. So if I subtract 720, 865 minus 720 is 145. Where does 145 land? Quadrant 2, so 145 is there. How much more do I need to reach the x-axis? So 180 minus 145. Reference angle would be 35 degrees. Oops. Okay, now you think radians might be more difficult, but it's actually a lot easier to deal in radians. 3 pi over 4. Where does that land? Quadrant 2. How come? It's 1 less than 4/4. So 3/4 is going to be right there. Well, we've already answered what the reference angle is. We said the difference between 4/4 and 3/4 was 1. So this is just 1 pi over 4, or you can leave that off and just say pi/4. Because to get from 3 over 4 to 4 over 4, we need 1 over 4. All right? What about negative 8 pi over 5? Where is that going to land? Is it bigger than 1 pi? Yes. Is it bigger than 2 pi? No. So we're going backwards. How far to there? 5 over 5. How far to here? 10 over 5. So am I closer to negative 5 over 5 or negative 10 over 5? Closer to 10. So it would be quadrant 1. If that is negative 8 over 5, what's my reference angle? Wait a minute. 2 over 5. Because reference angles are always positive. So I need 2 more fifths to get back to the x-axis. Okay? Let's do a big one. 23 pi over 3. So let's count this off. 3/3, 6, 9, 12, 15, 18, 21, 24. So this was 21/3, and this was 24/3. Which one am I closer to? 24/3, so I'm in quadrant 4. How much more do I need to finish the circle? 1/3. So reference angles are actually a lot easier in radians than they are in degrees because you don't need a calculator. All right? Are we okay with coterminal angles? So you either add 360 or subtract 360, or you add 2 pi or subtract 2 pi. Because on the back side of this worksheet, you have coterminal angles. Okay, that's everything you need to know. If you need help, raise your hand. I'll come help you.